Today, I want to start with a simple, slightly unsettling idea. The universe is not just out there, it's also a record, and we're learning how to read it better every year. And I don't mean that in a poetic way, I mean it literally. We collect signals, we compare numbers, we argue about error bars, and then we change our minds, sometimes fast. Just to anchor us in the present for a second, as of November 18, 2025, the LIGO-Virgo-Cagra collaboration wrapped up its fourth observing run, 04, meaning we're not only looking at the universe, we're listening to space-time shake when black holes collide. Around the same time frame, ESA's Euclid mission has begun releasing survey data built for one big goal: map the large-scale structure of the cosmos and help us pin down what dark stuff is doing, dark matter, and especially dark energy. And then there's DESI, a ground-based survey that has been testing whether dark energy is truly constant or whether it changes with time. Some recent public summaries have said the data, when combined with other measurements, can lean toward the "it evolves" option, which would be a big deal if it holds up. Meanwhile, the James Webb Space Telescope keeps pushing our view toward the early universe, including record-breaking distant galaxies, objects seen only a few 100 million years after the Big Bang, so the baby pictures of the cosmos are getting less blurry. So yeah, this is not a quiet moment in astronomy. But here's the twist. The story we're going to tell today is not mainly about new gadgets or even about new facts. It's about a pattern. Over and over, humans build a picture of the universe that feels reasonable, and then one measurement comes along and makes that picture feel cramped, too small, too confident, and then we revise it. The lecture is a guided tour of those revisions, from ancient sky stories and early geometry, through the sun moving to the center, through Newton's gravity, through Einstein's spacetime, all the way to an expanding universe, a hot beginning, and the modern question that still bugs everyone. What is driving the acceleration of cosmic expansion, and do we actually understand it? Or are we just labeling our ignorance with a nice name? If you're listening to this before sleep, just let that question hang around quietly in your head. We'll come back to it, because it's basically the link between all the chapters. So maybe subscribe and tell me where you're watching from and what time it is. I always check the comments, and it's fascinating seeing New York on a coffee break and London winding down for the night. All at once, all of us wondering about the same mysteries. Before we jump back to the ancient world, let's spend a little time in the present, because modern cosmology is not just one big idea, it's a bunch of new kinds of evidence arriving almost at once, and it changes how confident we are and what we even argue about. For example, on November 18, 2025, the LIGO-Virgo-Cagra collaboration officially wrapped up its fourth observing run, 04, which matters because gravitational wave detections aren't just cool signals, they're a whole new census of extreme objects, black holes and neutron stars. And they let us test gravity in conditions we can't build on Earth. At the same time, we're also doing a quieter kind of revolution, the survey revolution, where you stop obsessing over a few famous galaxies and instead map millions of them, patiently. And in that lane, ESA's Euclid mission released its first batch of survey data on March 19, 2025, including previews of deep fields and the kind of galaxy shape measurements that feed weak lensing maps, which is basically how we trace dark matter without ever seeing it directly. And then there's DESI, the Dark Energy Spectroscopic Instrument, which had a major unblinding set of results in December 2024, publicly discussed in 2025. And the careful headline there is not, "We solved dark energy." It's more like, when we combine DESI with other datasets like the cosmic microwave background and Type 1a supernova distances, the data can prefer a model where dark energy changes with time. And that's a big deal if it holds up. But it's also exactly the kind of claim scientists treat with caution, because surveys get stronger as they grow. And meanwhile, the James Webb Space Telescope keeps pushing the frontier of early cosmic time, with spectroscopically confirmed galaxies at extremely high redshift, like JADE's GS Z14-0 at about Z equals 14.32, which corresponds to less than 300 million years after the Big Bang. And that's not just trivia. It puts real pressure on our models of how quickly the first luminous structures could form. So, if you're listening to this at night, half asleep, here's the simple takeaway you can keep without effort. We now have multiple, independent ways to check our story about the universe. We can listen with gravitational waves, we can map with giant surveys, we can look farther back with infrared telescopes. And the reason this matters for a history lecture is that every time the evidence gets richer, the universe usually turns out to be a little less neat than the last generation hoped. And that's exactly how the subject keeps moving. Let's rewind gently, without rushing, to the ancient world, because this is where the basic habits of cosmology were formed, the habits we still carry today, even when we pretend we don't. Back then, the sky was not space. It was a ceiling, a calendar, a navigational tool, and also a kind of authority. And different cultures tracked it for different reasons, but one thing is consistent. If you watch long enough, patterns show up, and once patterns show up, you start building explanations around them. In the Mediterranean world especially, the explanation that took over was geocentrism, the idea that Earth sits still at the center, while the sun, moon, planets, and stars move around it. And I know that sounds obviously wrong to us now, but try to feel how reasonable it is from the ground, with no telescope, no photos, no rockets, just your eyes and a lifetime of careful notes. The stars do look like they swing around you each night. The ground does feel still, and the simplest story is that everything else is moving. The Greeks in particular leaned into geometry, and that was a huge step, because it meant the heavens could be described with rules, not just myths. And you can see that shift in models like Eudoxus's homocentric spheres, basically nested spheres sharing the same center, Earth, each sphere turning in a uniform way so that when you combine motions, you can reproduce the weird things people actually see, like retrograde motion, when a planet seems to back up against the background stars for a while. It's not perfect, but it's a real attempt to save the appearances using math. And that phrase matters because it hints at something very modern. A model can be judged by whether it matches observations, even if you're not totally sure what's physically real. Aristotle then takes this mathematical tendency and turns it into a full physical worldview, a cosmos that is finite, spherical, and organized in layers, with Earth near the center, and the outer boundary often described as the region of the fixed stars, and beyond that, not much that humans can meaningfully talk about, at least not in a scientific way. The important historical point is that Aristotle's universe is not just a picture, it's a system. It comes with ideas about natural motion, about why things fall, about why the heavens move in circles. And once you have a complete system like that, it becomes extremely persuasive because it explains many different things at once, not only where planets are, but what motion even is. And still, people were doing hands-on measurement too, not just philosophy. And a classic example is Eratosthenes, who used the fact that at noon on the summer solstice, the sun is nearly overhead in Cyrene, while it casts a measurable shadow in Alexandria. And with that angle and the distance between the cities, he estimated Earth's circumference, which is wild when you think about it, because it means the Earth is a measurable object, not just a mythical foundation. You can put a number on it. Now, if you're listening to this late, half asleep, here's the calm takeaway. Ancient cosmology wasn't one single idea, it was a toolkit forming, slowly. Careful watching, long records, geometry, and this growing confidence that the sky follows rules. And then, around the 2nd century CE, Ptolemy delivers the most successful version of the geocentric program, the Ptolemaic system, which uses combinations like deference and epicycles, and crucially the equant, to match the observed uneven speeds of planets in a way that is mathematically flexible and, for its time, impressively accurate. It's also a great historical lesson because it shows how a model can become dominant, not because it is true in the deepest sense, but because it works, it predicts, it organizes a messy sky into something you can calculate. And if you want a physical symbol of that calculating culture, something you can picture even with your eyes closed, think of the Antikythera mechanism, a Hellenistic-era geared device built to track astronomical cycles and predict things like eclipses, basically an analog computer, centuries before anyone expected such machinery to exist. So by the time we leave the ancient world, we're not leaving behind ignorance. We're leaving behind a sophisticated, practical, and very human approach to the cosmos. Build a model that fits what you see, keep refining it, and trust the mathematics more than your gut, even if your gut keeps whispering, but it feels like we're at the center. Okay, we move into the early modern period, and the big change here is not that people suddenly got smarter, it's that they started building habits that made it harder to fool themselves. More measuring, more checking, more math, and honestly, more arguing in public about what counts as evidence. What we call the scientific revolution, mainly across the 1500s and 1600s, is that shift toward quantitative thinking, toward treating nature like something you can test instead of just interpret. And the telescope is the obvious symbol. In the fall of 1609, Galileo starts using telescopes strong enough to really matter, and pretty quickly the sky stops behaving like an unchangeable, perfect realm. He sketches the moon and it doesn't look smooth. It looks rough, uneven, like a real place. Then in January 1610, he sees 4 moons going around Jupiter, which is a quiet little disaster for the old everything circles Earth vibe, because here are bodies clearly orbiting something else. And then there's Venus, which is even more decisive in a way that's kind of simple. Galileo observes the phases of Venus, and that observation is direct evidence that Venus orbits the Sun, because the geometry of the phases just doesn't work in the old Ptolemaic setup. None of this instantly settles the whole universe. People fight over interpretation, people fight over authority, but the direction changes. And at almost the same moment, you get Johannes Kepler taking Tycho Brahe's data and doing the thing that feels boring, but is actually revolutionary. He lets the math tell him what shape the orbit is, even when it ruins the aesthetic of perfect circles. He announces his first two laws in 1609 and a third law a bit later, and suddenly planetary motion is not just a story, it's a set of precise relationships you can calculate. If you're listening to this before sleep, keep one calm point. This era is when the sky becomes a laboratory, not in the sense that people can touch it, obviously, but in the sense that claims about the heavens start living or dying based on observations that other people can repeat, with instruments, with numbers, and with models that have to face the data. Now we get to the moment where the center shifts, at least for the solar system. And it happens in a way that's more careful and more human than people imagine. In 1543, Nicolaus Copernicus publishes De Revolutionibus, and what he's really offering is a new layout for the heavens, with the sun placed at the center of the system and Earth turned into a moving planet. It's not a mic drop event where everyone instantly agrees. A lot of readers treat it as advanced mathematics, useful for calculation while still keeping their old physical intuition in the background. And that's important, because historically, the Copernican idea spreads first as a better way to organize planetary motion, and only later as a new picture of reality. You also get, almost right away, a kind of middle path, the Tychonic system, where Earth stays fixed at the center, the Sun and Moon go around Earth, but the other planets go around the Sun. So you can keep the old feeling of stability, but borrow the Copernican geometry where it helps. That compromise tells you how hard it was to let Earth move. Then the 1600s pushed the issue from nice math into, okay, what do we actually believe? Galileo plays a big role here. His dialogue, published in 1632, sets up an argument between worldviews, and it's not subtle about which side sounds smarter. And in 1633, he's summoned to Rome and tried by the Inquisition, which turns a scientific question into a public, political, and personal crisis, the kind of thing people remember for centuries. Meanwhile, Kepler is doing the quieter work that makes the sun-centered system feel less like philosophy and more like a machine you can compute. He publishes the first two laws in 1609 and the third in 1619, and those laws say plainly that planets move in ellipses with the sun at a focus, and that their speeds change in a very specific way. And then in 1627, he publishes the Rudolphine Tables using Tycho's observations, and prediction becomes dramatically better, which is the part that convinces working astronomers. So if you're listening to this late at night, here's the soft landing. The sun moving to the center wasn't one heroic moment. It was a slow transfer of trust from an Earth-centered intuition to a sun-centered framework that kept winning on accuracy and eventually on confidence. Now let's ask the question that sounds abstract, but historically it was almost unavoidable. Is the universe infinite? Or is it more like a closed room, a big but bounded shell of stars? For a long time in Europe, the closed room idea felt natural because it matched the old picture of crystalline spheres and a finite cosmos. But in the late 1500s, the mood starts to shift. In 1576, the English thinker Thomas Digges takes the Copernican framework and pushes it further, suggesting the fixed stars are not glued onto one last outer sphere, but are spread through endless space. And he publishes that kind of language and imagery in English, which matters because it makes the idea portable. And then Giordano Bruno goes even more radical in 1584, arguing for an infinite universe with many worlds. And again, we're not talking about a telescope proof here. We're talking about a philosophical move that tries to take the Copernican displacement seriously, all the way. Still, even before you can test infinity directly, the night sky quietly starts to complain. Because if the universe were infinite in size, and also eternal, and also roughly uniform, and also filled everywhere with stars, then in principle every line of sight should end on a star, and the sky should look bright in every direction, not mostly dark. This is what later gets called Olber's paradox, and the key point for us is not the name. The key point is what it does to your confidence. It tells you that at least one of those assumptions has to give. Maybe the universe has a finite age, so light from the farthest regions simply hasn't had time to reach us. Maybe the universe is not static, so light gets stretched and diluted by expansion. Maybe stars don't fill space uniformly, or they don't shine forever. In modern cosmology, the clean resolution combines ideas like finite cosmic time and redshift from expansion, and it even ties into the fact that the bright, everywhere background we should expect is not invisible light at all. It's largely been shifted down to the microwave background temperature, around 2.7 Kelvin. So, if you're listening to this late, here's the gentle takeaway. The infinite universe question isn't a yes or no button, it's a stress test. Once you take it seriously, you're forced to admit the universe can't be an eternal, unchanging stage with stars sprinkled forever. It has a history. And that single shift from timeless to time-full is basically the doorway into modern cosmology. Picture the universe as it looked to educated Europeans in the late 1600s. People had good data on planetary motion thanks to Tycho Brahe and Kepler, but the why still felt slippery. And then Newton happens. The spark, historically, is that in 1684, Edmund Halley goes to Cambridge to ask Newton a very specific question that was floating around the Royal Society crowd. If gravity falls off like the inverse square of distance, what kind of orbit do you get? Newton's answer, basically, is an ellipse. Not because he guessed, because he had already done the math. And that question turns into a manuscript, and that manuscript turns into the Principia, published in 1687, with Halley pushing, editing, and even helping get it into print when funding was tight. The important part is what Newton unifies. He gives you laws of motion that treat the heavens and the earth the same way, and he gives you universal gravitation as a rule that can connect those laws to actual astronomical paths. So Kepler's laws stop being just beautifully accurate patterns and start looking like consequences. The orbit shapes, the changing speeds, the whole rhythm of the planets suddenly fits inside one framework. And Newton doesn't sell it as a cosmic poem, he sells it like a hard-nosed accountant. If you accept these laws, you can compute, you can predict, you can check. He even builds intuition in a way that feels modern. A planet is like a projectile that never stops falling because it keeps missing the Earth. That's the clean mental image. And then the Principia keeps piling on reality checks. The moon's motion isn't a separate kind of thing. It's the same gravity that makes objects fall near Earth, just weakened by distance. Tides become part of the same conversation because they're about differential gravity across Earth's diameter. And comets stop being supernatural visitors and start being objects with trajectories you can, at least in principle, calculate. This is the moment where the universe follows rules turns from a slogan into a working practice. But Newton also leaves a small, honest gap, and I like keeping it in the story because it prevents hero worship from turning into mythology. Newton can write down the force law and show it works, but he resists claiming he knows the physical mechanism behind gravity acting across empty space. In his correspondence with Richard Bentley in 1692 to 1693, He calls the idea that gravity is innate to matter, letting one body act on another through a vacuum, so great an absurdity unless some mediation exists. And later, in the General Scholium added to the 1713 second edition of the Principia, he's famous for hypotheses non fingo. Basically, I'm not going to pretend I have a mechanism when what I have is a law that reliably matches phenomena. So the Newtonian universe is both confident and cautious at the same time. The math works, the deeper cause is left open. Now, here's the next step that people often skip in the retelling, but it matters historically. For decades after Newton, gravity is a powerful rule, but its overall strength is not something you can measure directly in a lab. It's there in planetary motions, but not pinned down as a number you can dial in. That changes with the torsion balance experiment carried out by Henry Cavendish in 1797 to 1798, using an apparatus concept originally devised by John Michell. Cavendish's goal, as he framed it, was weighing the Earth, meaning estimating Earth's mean density, and only later did physicists rewrite the result in the language of the gravitational constant, g. The point is that Cavendish makes Newton's gravity feel even more real because it becomes measurable between objects on a table, not only inferred from the sky. And that's a quiet psychological shift. Gravity goes from a law that explains planets to a force you can detect in the lab with careful patience. So this chapter ends with a calm kind of clarity. Newton ties Earth and heaven to one rule. Cavendish helps turn that rule into something you can put numbers into. And once you have that, it becomes very tempting to think the cosmos is basically stable and finished. Historically, that temptation is exactly what the next generation leans into, right up until new observations force the universe to start moving again. After Newton, it became really tempting to picture the universe as a stable system that basically just sits there. Not because people were lazy, because the physics looked clean and the observations were limited. And honestly, a changing universe creates awkward questions. For most scientists in the 1800s and even into the early 1900s, the default assumption was that the universe on the largest scales is static, not expanding, not contracting, just more or less the same forever. And there was a practical reason for that too. For a long time, the universe was basically what you could map as a stellar system, and many astronomers treated the Milky Way as the main thing, maybe even the whole thing, while whatever was beyond it was left vague or left to philosophy. You can see this in late 19th century and early 20th century thinking, where the material universe is often described as a finite stellar system sitting inside an infinite Euclidean space, with the Milky Way as the obvious candidate for that system. So the cosmos is big, sure, but not obviously evolving. But the static picture had Kenshin baked into it. Newtonian gravity is attractive and long-range. If you take a uniform matter distribution and ask for a truly static infinite universe, gravity doesn't politely cancel out in a stable way. It tends to collapse, or it creates mathematical headaches about the gravitational potential in an infinite space. People noticed this. Some proposed that the distribution of matter is not infinite. Others tried small modifications to the force law at very large distances, like the kind of ideas associated with Seeliger, basically to keep an infinite universe from becoming mathematically pathological. And still, the broader culture of cosmology stayed conservative. Static felt safer. Static avoided the beginning problem. It also matched what the sky looked like if you didn't yet know that those faint spiral nebulae were separate galaxies at huge distances. So if you're listening to this late, here's the quiet point. A static universe wasn't a silly belief. It was the simplest working guess given the evidence people had. But it was also unstable as an idea. It needed patches, and once better observations arrived, that calm, unmoving cosmos would be the thing that finally, and kind of abruptly, had to give. The story slides into the early 20th century, and this is where cosmology starts to feel less like star lore and more like physics with receipts. Because two things happen at once. We realize the universe is bigger than the Milky Way, and we get a new theory of gravity that can talk about the whole universe in one set of equations. On the bigger than the Milky Way side, there's a very American moment in 1920, the Shapley-Curtis debate in Washington, D.C., basically arguing whether those spiral nebulae are nearby objects inside our galaxy or separate island universes far beyond it. It sounds like a niche academic fight, but it's really a fight over what the word universe even means. Then the evidence starts turning. Vesto Slipher at Lowell Observatory had already been measuring radial velocities of spiral nebulae starting in 1912, and the numbers were weirdly large, which quietly suggested these objects might not be small local clouds at all. And then Edwin Hubble comes in with the cleanest kind of astronomical proof. By 1924, he identifies Cepheid variables in Andromeda, uses the period luminosity relation, and gets a distance so large that Andromeda can't reasonably be part of the Milky Way. It's another galaxy. So, okay, the universe just got dramatically larger, almost overnight in cultural terms. Now, on the physics runs the show side, Einstein's General Relativity arrives in 1915, and then in 1917 he applies it to the universe as a whole and tries to keep the universe static by adding a cosmological constant, because without it, gravity tends to make a universe collapse. In the same era, de Sitter finds a relativistic solution that can produce redshift effects, which makes people think, wait, maybe redshift is not just a Doppler trick from motion, maybe geometry is involved. Then Friedman, in 1922, shows something blunt and important. Einstein's equations naturally allow expanding or contracting universes. You don't have to force the universe to sit still. And in 1927, Georges Lemaitre takes the next step and connects theory to observation using galaxy redshifts and arguing for an expanding universe, even estimating an expansion rate. And finally, in 1929, Hubble publishes the distance-velocity relation for galaxies, showing a roughly linear trend. That's the moment the expansion idea stops being a clever solution on paper and starts looking like a property of the real sky. So if you're listening to this late, here's the quiet takeaway. The Universe in the Hands of Physics chapter is basically when the universe becomes measurable in scale and dynamical in time. It's no longer a static backdrop, it's a system with an evolution, and the math and the telescope start agreeing often enough that you can't ignore it. We can finally talk about Einstein, and I'll do it without the scary math, because for history, the key is the shift in intuition. In 1905, Einstein publishes his special relativity paper on the electrodynamics of moving bodies, and it quietly changes the rules of the game. Space and time stop being separate, rigid things. The speed of light becomes a kind of fixed limit. And if you're drifting off a bit, you can hold just this. Measurements of time and length depend on motion. Not because anyone is cheating, because nature is built that way. Then, a few years later, he goes after gravity, and the core move is the equivalence idea, the feeling that free fall and weightlessness are closely related, like gravity and acceleration are two sides of the same coin. And by late 1915, with full publication following in 1916, general relativity appears as a new theory of gravity. Gravity is no longer a force pulling across space, it's the geometry of space-time itself. Matter and energy shape space-time. Space-time tells matter how to move. It sounds philosophical, but it cashes out into very specific predictions. One is the extra precession of Mercury's orbit. Another is that light should bend when it passes near a massive object like the Sun. And the famous public test comes in 1919 during the total solar eclipse of May 29, with expeditions organized to measure starlight deflection near the Sun. The results were announced later that year, and suddenly Einstein becomes a household name. Which is kind of funny because the public story is dramatic, but the deeper story is slower. Relativity wins because it keeps surviving tests and because it gives physicists a language that works from apples to galaxies. And then comes the part that matters for cosmology. Once you have general relativity, you can't treat the universe as a static stage without checking whether the equations even allow it. In 1917, Einstein applies general relativity to the universe, and because he expects a static cosmos, he introduces the cosmological constant term. It's basically a way to counteract gravitational attraction on the largest scales so the universe can sit still. That's the historical irony. The same framework that makes expansion feel natural also contains a knob you can turn to try to avoid expansion. So if you're listening to this before sleep, here's the calm takeaway. Einstein didn't just add a new chapter to physics, he changed what gravity is. And the moment gravity becomes geometry, the universe stops being something you can assume is steady. You have to ask what space-time is doing, expanding, contracting, or something even stranger. Now we're in the part of the story that sounds like science fiction, but it actually starts as paperwork in physics journals. Black holes show up in general relativity almost immediately. In 1916, Carl Schwarzschild writes down the first exact solution to Einstein's equations for a simple spherical mass, and that solution contains the basic ingredients of what we now call a black hole, including the idea of an event horizon. People argue for decades about what's real and what's just coordinates, because early relativity is full of those traps. Then, in 1939, Oppenheimer and Snyder publish a model of continued gravitational collapse, basically saying, look, if a massive star runs out of pressure support, collapse is not just a story, it's a solution of the equations. The name black hole comes later. John Wheeler popularizes the term in 1967 because gravitationally completely collapsed object is not a phrase anyone wants to repeat all night. And what's nice, historically, is that black holes eventually move from theory into direct evidence. In 2016, the LIGO team publishes the first direct detection of gravitational waves, GW 150914, from a binary black hole merger. So we're not just imagining black holes, we're literally measuring what they do when they crash together. And in 2019, the Event Horizon Telescope releases the first image of a black hole's shadow, M87*, which is another kind of reality check. Visual this time, not just a signal in a detector. Now, wormholes are a different vibe. The earliest famous version is the Einstein-Rosen bridge in 1935, a mathematical connection between regions of spacetime that looks like a tunnel on paper. But paper is generous. Most wormholes, as written, aren't stable or traversable in any comfortable way. In 1988, Morris and Thorne write a very influential teaching paper about traversable wormholes and what they would require. And the requirement is awkward. You typically need exotic matter, meaning you have to violate familiar energy conditions in general relativity, at least in some averaged sense. So, if you're listening to this before sleep, here's the calm, practical point. Black holes are now solid astronomy. We detect them, we image their environments, we do population studies. Wormholes are more like a stress test for our theories, a way to learn what the equations permit and what physics probably forbids. And when people talk about time travel in this context, it's usually a speculative add-on, not something we can claim the universe actually builds for us.
Here's where the universe stops being a fixed backdrop and starts acting like something alive in time. Not alive like a creature, just not frozen. The key idea is simple to say and weird to picture. Space itself can stretch. So when we say galaxies are receding, it's often not like bullets flying through space. It's more like the distance between calm, mostly stationary points is growing because the ruler is changing. Historically, the groundwork is laid in the 1920s. In 1927, Georges Lemaitre publishes a paper that takes the dynamic solutions of general relativity seriously and connects them to the observed redshifts of galaxies, basically saying an expanding universe can account for what we see, and he even estimates an expansion rate. 2 years later, in 1929, Edwin Hubble publishes the famous distance-velocity relation for galaxies, showing that the farther a galaxy is, the larger its redshift-derived recession speed tends to be, roughly in a linear way, at least over the range he could measure. And that's the turning point, culturally and scientifically. Expansion stops being a theoretical option and becomes a property of the sky. If you want one clean sentence for this whole chapter, it's this. In an expanding universe, light gets stretched while it travels, and that stretching shows up as cosmological redshift. Modern cosmology writes it compactly as a link between redshift and the cosmic scale factor, meaning the size of the universe when the light was emitted compared to now. You don't need the formula to feel the consequence. Farther means earlier, and earlier means denser and hotter, which sets up the next chapters. Also, a small historical note that matters in the US classroom. In 2018, the International Astronomical Union recommended calling this relation the Hubble-Lemaitre law, partly to reflect Lemaitre's role in the story, not only Hubble's. And then, because this is still a lively science, there's a modern wrinkle you can mention without going deep. When we measure today's expansion rate, the Hubble constant, different methods still don't perfectly agree, and that mismatch is what people call the Hubble tension. Webb and Hubble together have been used to cross-check one major source of possible error, Cepheid distance measurements, and the result is basically the puzzle doesn't go away just because you upgraded the camera. So if you're listening to this late and you want the soft takeaway, the changing size of the universe is the moment cosmology becomes a story with a timeline, not just where things are, but how the whole stage itself changes, slowly, steadily, and maybe with a few surprises still waiting. Here's the thing. Once you accept that the universe is expanding, you don't get to keep the past comfortable. You automatically get a past that is smaller, denser, and hotter. And hot here is not a mood word, it's a physical condition, because temperature is just a way of talking about the typical energies of particles and radiation. So the hot Big Bang idea is basically the universe having a real thermal history, like a timeline of cooling, where the rules of nuclear physics and particle physics actually matter. Historically, this takes shape in the 1940s, when people like George Gamow, Ralph Alpher, and Robert Herman start treating cosmology as something you can calculate, not just describe. They ask a very blunt question. If the early universe was hot and dense, could it make the first chemical elements before there were stars? And the answer is yes, but only the light ones, and only during a short window. In April 1948, Alpher, Beta, and Gamow publish The Origin of Chemical Elements, and the paper is famous partly because Hans Bethe's name turns the author list into a joke, alpha, beta, gamma. But the science point underneath is serious. You're trying to build a chemical forecast from first principles in a universe that is cooling as it expands. Now here's the part people sometimes miss. Big Bang nucleosynthesis, BBN, is not the universe made everything. It's more specific than that. It mostly sets the primordial amounts of hydrogen and helium, with small leftovers of deuterium, helium-3, and lithium-7. And it has a built-in stopping point because the early universe expands fast and because nuclear physics has a bottleneck. There are no stable nuclei with mass number 5, and that blocks an easy path to heavier elements. So heavy stuff like carbon and oxygen needs stars later. So BBN is an early chapter, not the whole chemistry book. If you want to feel the timing without getting lost, think in rough stages. First, at very early times, everything is a hot plasma, a soup of photons, electrons, positrons, neutrinos, and nucleons. At temperatures around the MeV scale, weak interactions keep neutrons and protons flipping back and forth, and the neutron-to-proton ratio is set by that balance, plus the fact that neutrons are slightly heavier. As the universe cools, those weak reactions slow down, and at about 1 second or so, the neutron-to-proton ratio freezes out, meaning it stops tracking equilibrium. A useful mental picture is that the universe cools faster than the reactions can keep up, so the ratio gets locked in, roughly around 1 neutron for every 6 protons at freeze-out, and then it drifts a bit because free neutrons decay with a lifetime of about 15 minutes. That decay matters because BBN doesn't immediately start making stable nuclei. This brings us to the bottleneck. Even though protons and neutrons can in principle form deuterium, deuterium is weakly bound, and the early universe has an enormous number of high-energy photons compared to baryons. So any deuterium that forms gets immediately smashed apart. People call this the deuterium bottleneck, and it's one of those phrases that sounds fancy but really means something simple. You can't build heavier nuclei efficiently until the universe cools enough that deuterium survives. That happens when the temperature drops to around 0.1 MeV, which corresponds to a few minutes after the beginning of the expansion history we're describing. Then things move quickly. Once deuterium can stick around, nuclear reactions run for a short burst, converting most available neutrons into helium-4 because helium-4 is very tightly bound. That's why helium is the big product. And this is where the famous about a quarter of the mass ends up as helium-4 comes from. It's not a random number someone chose. It comes from the neutron fraction at the start of nucleosynthesis, plus the fact that almost every surviving neutron winds up in helium-4, because that's the energetically favored endpoint for light nuclei in that environment. So the universe exits this phase with mostly hydrogen by number and about 25% helium by mass.
plus leftover deuterium and helium-3 at trace levels, and lithium-7 at an even smaller level. And then, about 20 minutes after the start of BBN, expansion wins. The density and temperature drop too low, and fusion basically shuts off. The universe keeps cooling, but it's done making new nuclei in bulk until stars arrive much later. This is why BBN is often called one of the deepest reliable probes of the early universe. It uses standard, well-tested physics, and it makes predictions you can compare to observations.
And those comparisons are not just philosophical. Deuterium, for example, is incredibly sensitive to the baryon density. More baryons means deuterium gets burned into helium more efficiently, so the leftover deuterium abundance acts like a kind of baryometer. Helium-4, on the other hand, is less sensitive to reaction details and more sensitive to the expansion rate and the neutron-to-proton ratio, so it tests a different piece of the story. Lithium-7 is where things get annoying because observations and standard predictions have had a long-running mismatch, the so-called lithium problem, which is one reason cosmologists stay humble when they say the model works. It mostly works. It also has cracks. Now, there's another almost too neat historical twist here, and it connects directly to your next chapter on the cosmic microwave background. If the early universe was hot and filled with radiation, then as the universe expands, that radiation should cool but not disappear. In 1948, Alpher and Hermann explicitly estimate a present-day background temperature on the order of 5 Kelvin in their Nature paper, Evolution of the Universe, which is remarkably close in spirit to the later measured value, even though the idea didn't become mainstream right away. And it's worth saying why it didn't. People didn't have the right instruments yet, and the community's attention was split, including steady-state alternatives and just the basic problem of mapping galaxies. But the logic was sitting there waiting. Hot, early universe implies leftover cooled radiation. So if you're listening to this late, here's the gentle takeaway you can keep without effort. This chapter is where cosmology stops being only geometry and gravity and becomes thermodynamics and nuclear reactions too. The universe becomes something you can audit in a sense. You can check it. The hydrogen and helium around us carry a memory of the first few minutes, and the sky itself, as we'll see next, carries a memory of the early heat in the form of a faint, cold glow that fills all space. The cosmic microwave background, the CMB, is a turning point because it's not just a clever argument, it's the universe showing you its paperwork. The logic is simple. If the early universe was hot and dense, it was full of light, not starlight, just thermal radiation everywhere. And if space expands, that light gets stretched and cooled, so today it should show up as a cold microwave glow across the entire sky. In the late 1940s, Ralph Alpher and Robert Herman said, basically, you should expect a leftover background at only a few Kelvin, and they were right in spirit long before the technology caught up. Then in 1964 and 1965, Arno Penzias and Robert Wilson at Bell Labs run into this stubborn hiss in their horn antenna that won't go away, no matter what they clean or calibrate. And it turns out to be real sky signal, almost perfectly uniform. At almost the same moment, Robert Dickey's group at Princeton is thinking about exactly this predicted background, so the interpretation lands quickly, and the Big Bang stops being just the storyline and starts looking like a testable physical past. But here's what makes the CMB more than one famous discovery story. It's a snapshot of a specific time. Roughly 380,000 years after the Big Bang, the universe cooled to around a few thousand Kelvin. Electrons and protons could finally stay together as neutral hydrogen, and the universe became transparent, meaning photons stopped bouncing endlessly off free electrons and started traveling freely through space. Those are the photons we still see today, coming from what people call the surface of last scattering, like a fog lifting, and suddenly you can see the wall behind it. When Kobe flew later, it did the kind of check you can't really argue with. FIRIS measured the CMB spectrum and found it is an almost perfect blackbody, which is exactly what you'd expect from a hot thermal origin, not from a patchwork of later sources. And then Kobe's DMR instrument found tiny temperature differences across the sky, announced in 1992. Not big variations, just enough to matter, because those tiny variations are the seeds that gravity can later grow into galaxies. After that, the game changes into precision mode. WeMap and then Planck map the anisotropies with much higher detail, and they don't just say, yes, there are spots, they measure a whole pattern. The peaks and dips in the angular power spectrum are basically the fossil record of sound waves in the early plasma, pressure fighting gravity, before the universe became transparent. And the exact shape of that pattern lets you infer real things, like how much ordinary matter there is, how much dark matter there is, and how the universe's geometry behaves. Planck's legacy is that it constrains that pattern extremely well, with many acoustic peaks measured in both temperature and polarization. And that's why modern cosmology can pin down a consistent parameter set instead of just arguing in circles. And if you want one calm number to keep in your head, the mean temperature of the CMB today is about 2.72 Kelvin. So the gentle takeaway is this: the CMB is the quietest, loud evidence we have. It's the afterglow of a real hot phase. It's a photo of the universe when it was young, and it's a toolbox that lets us read the universe's composition and early behavior without guessing. By the late 1970s and early 1980s, the hot Big Bang model is doing a lot of things right, but it's also carrying a couple of quiet headaches that won't go away, like why the universe looks so nearly flat, and why regions of the sky that were never in contact still have almost the same temperature, the so-called flatness and horizon problems. Then in 1981, Alan Guth proposes cosmic inflation, basically a very early burst of accelerated expansion, and the point is not to make the story more dramatic, it's to make the initial conditions less unbelievably fine-tuned. Inflation takes a tiny, causally connected patch and stretches it so much that it can look flat and uniform on the scales we observe, and it also dilutes unwanted relics that were bothering particle physicists, like certain heavy defects. After Guth, the idea evolves fast. There are different versions and different mechanisms, including models associated with André Linde, like chaotic inflation in 1983, and another influential route where inflation comes from modifying gravity, the kind of approach connected to Starobinsky's early work. And then there's the part that makes inflation feel less like a patch and more like a generator of structure. Quantum fluctuations, tiny random wiggles at microscopic scales, get stretched up to cosmic scales during inflation, and later they become the seeds of galaxies and clusters. This sounds almost magical when you say it quickly, but observationally it leaves fingerprints, especially in the pattern of tiny temperature variations in the cosmic microwave background. Planck's 2018 analysis, for example, finds a scalar spectral index around 0.965 and tight limits on primordial gravitational waves, and overall it's pretty consistent with a simple, slow-roll-style inflation picture, while also ruling out a bunch of easy toy models people used to like. So, if you're listening to this late, here's the calm takeaway. The Big Bang part of the story says the universe had a hot, dense early phase and has been expanding and cooling ever since. Inflation is like a preface, a short episode that might set up the initial conditions for that hot phase, and then hand the universe off to reheating, where the energy driving inflation gets converted into the hot soup of particles and radiation. And one small historical note, just because people ask. The phrase Big Bang was coined by Fred Hoyle in a BBC radio broadcast on March 28, 1949, and even though it started as a catchy contrast with steady-state ideas, it stuck, and it's still the label we use for a theory that is really about expansion and thermal history, not an explosion in empty space. Here's the twist that turned late 1990s cosmology into a different kind of science. For most of the 20th century, the reasonable expectation was that cosmic expansion should be slowing down, at least gradually, because matter attracts matter, and gravity is, by default, a brake. People argued about how much it should slow, not whether it should slow at all. Then the supernova results arrived and basically said, no, the brake isn't just failing, something is acting like a gentle accelerator. Two teams got there independently using distant Type 1a supernovae, the High Z Supernova Search Team in 1998 and the Supernova Cosmology Project in 1999. The headlines make it sound simple, but the method is worth hearing because it's where the trust comes from. A Type 1a supernova is a white dwarf explosion, and while they're not all identical, they're close enough that you can standardize them. The key trick is that the light curve shape carries information about intrinsic brightness. Brighter ones fade more slowly, dimmer ones fade faster. That relationship was formalized clearly in 1993 by Mark Phillips, and it becomes one of the practical foundations of using SNIA as distance indicators. So when observers build a Hubble diagram, they're not just eyeballing brightness, they correct for light curve shape, they deal with color, and they try to manage dust and selection effects. Then they compare what the universe actually does to what different cosmological models predict. And what those 1998-1999 data said, in plain language, was that many high redshift supernovae were dimmer than expected in a universe where expansion is simply coasting or slowing. Dimmer at a given redshift means farther away than you'd expect. Farther away means the universe had to expand more during the time the light was in transit, and that pushes you toward acceleration. Rees and collaborators framed their 1998 result as evidence for acceleration and a positive cosmological constant. Perlmutter and collaborators in 1999, with a larger sample, found the same basic story. This wasn't a small adjustment, it was a sign flip in the cosmic narrative. So what do you put into the equations to make expansion speed up? In the simplest language, you need something that behaves like negative pressure on large scales, something smooth enough that it doesn't clump the way matter does, and strong enough that as the universe expands, it doesn't dilute away quickly. People started calling that missing ingredient dark energy, a label that Michael Turner coined in 1998. And the label is honest because it names the problem without pretending we already know the substance. The simplest model for dark energy is also the oldest, Einstein's cosmological constant, a constant energy density associated with space itself. In the equation of state shorthand, that's W equals -1, meaning pressure is negative and equal in magnitude to energy density. That one parameter, W, becomes a kind of personality test for the universe. If W is exactly -1 and stays that way, you're in cosmological constant territory. If W differs from -1 or changes with time, then you're looking at a dynamical explanation. Things like scalar fields, often called quintessence in the popular naming tradition, or something even more exotic. And then there's the other big fork in the road. Maybe the acceleration isn't a new energy component at all. Maybe it's gravity behaving differently on the largest scales. That's the modified gravity option. Historically, the field has treated these as competing narratives that can mimic each other in certain datasets, which is why modern cosmology doesn't rely on one measurement anymore. It stacks probes. Supernova distances, the cosmic microwave background, baryon acoustic oscillations in galaxy clustering, weak gravitational lensing, growth of structure over time. The goal is to corner the explanation from multiple angles. And that brings us to why dark energy is still an active chapter, not a solved epilogue. The supernova story was persuasive, but scientists are trained to be paranoid in a productive way. They ask, could the supernovae themselves be changing over cosmic time? Could dust be tricking us? Could selection biases make distant samples look dimmer? Could host galaxy properties be correlated with corrected brightness? And the answer is, some of these effects exist, and people model them, and none of them so far has cleanly erased the acceleration signal across all the different lines of evidence. Also, as the years passed, the story got cross-checked by data that doesn't care about supernova astrophysics in the same way. The CMB gives you a picture of the early universe and a geometrical constraint on the cosmic inventory. Galaxy surveys measure clustering patterns that function like a standard ruler. Those pieces together in the standard framework strongly prefer a universe with a dominant smooth component today, consistent with dark energy. Planck's 2018 legacy results are a big part of that precision picture, because within base LCDM, they pin down a self-consistent parameter set that includes a dark energy-dominated late universe. So why are we still talking about this as a problem? Because the simplest explanation is also conceptually uncomfortable. If dark energy is vacuum energy, quantum field theory naively suggests a value that is wildly larger than what cosmology infers. And even if you don't want to go down that rabbit hole in a bedtime lecture, it's enough to say there's a deep mismatch between natural theoretical expectations and the measured cosmic acceleration scale. On top of that, the observational situation is getting more interesting again, in the very current sense. DESI, which builds a huge 3D map of galaxies and quasars and tracks how expansion behaved over billions of years, released public results in March 2025, stating that when combined with other data sets, the hints can strengthen for dark energy evolving with time, rather than being a perfect cosmological constant. That's not a final verdict. It's exactly the kind of cautious, data-driven discomfort that often precedes either a correction or a discovery. Euclid is also designed to attack the same big question by mapping the cosmic web and weak lensing with enormous statistical power. So the field is doing what it does best. It is trying to break its own favorite model, politely, with better evidence. If you're listening to this late,
Here's the calm takeaway. Dark energy began as a shock from supernovae. It matured into a standard model ingredient because multiple independent probes supported the same broad picture. And it remains a frontier because we still don't know what it is, and because the newest surveys are now good enough to test whether the simplest story, W equals -1 forever, is actually true, or just the best approximation we've had so far.
So where does all of this leave us? After myths, geometry, Newton, Einstein, expansion, a hot early universe, and then this weird acceleration. It leaves us in a place that's surprisingly honest. We know a lot, and we also know exactly what we don't know. We can measure the universe like never before, and at the same time, we're still arguing about what the main ingredients actually are. Dark matter, for example, shows up through gravity in galaxies, clusters, and lensing maps, but we still don't know what particle or field it is, or if it's something even stranger. Dark energy is even more awkward. We can track its effect through the expansion history, but we don't know if it's just a constant property of spacetime or something that changes over time. And the reason people keep pushing on this is not just curiosity. It's because the data keeps getting better. In March 2025, Euclid began releasing its first big survey products, built to map the cosmic web and lensing at enormous scale. And in the same month, DESI released new results that, when combined with other datasets, strengthened the hints that dark energy might evolve over time. Meanwhile, the universe also speaks in other channels now. As of November 18, 2025, the LIGO-Virgo-Cagra network completed its fourth observing run. So black holes are not just a chapter in theory anymore. They're part of our day-to-day evidence stream. And telescopes like Webb keep pushing us closer to the beginning, with record-distance galaxies like JADE's GS-Z14-0, reminding us that the early universe was already building structure fast. So the search for answers is not a vague slogan, it's a practical to-do list. What is dark matter? What is dark energy? Why do some measurements of today's expansion rate still disagree? What exactly happened in the earliest moments, and did inflation really happen in the way we tell it? How do we connect gravity to quantum physics without the whole story breaking? If you're listening to this before sleep, here's the quiet wrap-up. The history of cosmology is basically the history of shrinking our certainty and expanding our understanding at the same time. Each era replaces one comfortable picture with a better one. And the better one is usually less comforting, but more real. And that's fine, because the point isn't to end with a universe that feels simple. The point is to end with a universe we can keep learning from, slowly, carefully, one measurement at a time. And then, when we're tired, we can let the questions rest for a while. Because the sky will still be there tomorrow, doing what it does. Thank you so much for watching our video and supporting the channel. See you in the next episodes, and good night.